And that's how the tiling works. I'm not going to say anything more about it, really, but just to show the sort of way in which your understanding can be used, even though it isn't following an algorithm. So this is a way you would see how those tiles will tile the entire plane. I'm not going into the details of that, but you can see from the general nature of this picture how you could repeat this and repeat this at different sort of sizes of hierarchy, and you could therefore cover the whole plane. I want to mention this just as a current interest, because this subject is of current interest. Only very recently, a man called David Smith produced this shape that you can see, something's called the hat, and you see the shaded one in the sort of middle, slightly to the bottom left, right. And it's the same shape, sometimes turned over, mostly one way up. And it's very remarkable that this shape will only tile the plane in a way which never repeats itself, and in a way is even more subtle than the one that I showed you before. So you have to, this is sort of indicating how the level of sophistication, you may have an algorithm that works at a certain level, but it's never going to encapsulate one's entire understanding of how these things work. I don't want to go into that anymore because that was really the subject of my previous talk, but I thought I'd lead you into that a little bit. Okay, and the question then was, okay, if there is something non-algorithmic in how human brains work, and I would say conscious brains, and not just humans in my view, how conscious brains work, and how could that be part of the laws of physics? Because the laws of physics you could, in effect, put on a computer. There's a bit of a problem because you have to use the continuum rather than approximations to it. I don't regard that as the actual resolution of the issue. It seems to me that you can well enough model the continuum so that even though things like Newtonian mechanics even do depend on the continuum, you can approximate it by discrete calculations, and it's pretty well calculational. So Newtonian mechanics you could put on a computer. Maxwell's electrodynamics, a little bit more tricky, but you can put that on a computer too. Einstein's general relativity, more tricky still, but we have good evidence that it can be effectively put on a computer. The LIGO detector of gravitational waves detects signals which have been computed to indicate the inspiraling of black holes and so on. And so there are very, very powerful, precise calculations using general relativity, in general relativity to using computational techniques, so that it doesn't seem to be anything non-computational there again. What about the Schrödinger equation for the evolution of the quantum state? Again, there is something, a very deterministic and evolutionary computational equation with this, again, slight issue about being able to approximate the continuum with discrete calculations, but that doesn't seem to be the issue. But how about, just sort of by the process of elimination, the collapse of the wave function, which is something quite different. I should say also that this session is to do with determinism, or is that sort of issue. And the thing is, the collapse of the wave function, as we understand it, is not deterministic, but it's probabilistic. And just to say what it is, in quantum mechanics, you have this principle of superposition. You have two states, A and B are quantum states, might be states describing the world, and alpha and beta are complex numbers, ordinary real numbers, but with the addition of the square root of -1, if you don't know what complex numbers are. They're basic to quantum mechanics. You have to put them, those strange-looking numbers, but they're very clearly what the rules are about them and everything like that. So these complex numbers are not the problem. You can certainly put them on a computer just as well as you could put a real number. Again, by approximations, but that seems to be good enough. Now, what about the collapse of the wave function? Now, the Schrödinger equation preserves these superpositions, and I've got this in this picture here. Suppose A and B are two states, and A evolves by the Schrödinger equation A prime, and B evolves to B prime. Then the combination alpha A plus beta B, that's using the one I had in the previous slide, will evolve to alpha A prime plus beta B prime. So the alpha and betas remain the same. The amplitudes, as they're called, the complex amplitudes, which represent the how much of one state and how much of the other state is involved in this superposition, that remains constant, but A and B evolve according to the Schrodinger equation. But the collapse of the wave function is quite different. That happens when you make an observation on the system. It's a bit obscure what that really means. But if you make an observation on the system, then suddenly the things behave very differently. You take alpha and beta, you take their squared modulus, that means the square of the distance from the origin in the complex plane, where you represent the alpha and beta in this plane, and the ratio of those two squared moduli gives you the ratio of the probabilities of A and being the result, A or B being the result. So your measurement is supposed to decide whether your state is A or B, even though it's this superposition, and this superposition then tells you it's that probability mixture of A and B. It becomes a probability mixture, it becomes an indeterminate procedure, and that's the way standard quantum mechanics is argued to work. And these things are meant to be just probabilities. It doesn't say anything more than that. So you have this, well, there seems to be a role for free will, sometimes people say, because, well, the thing is not deterministic. I mean, there was the famous point of view introduced by Laplace after Newton had put forward his laws, and it seemed clear that if you knew what the complete state of the world was at any time, then the Newtonian equations would tell you what the state was the next 10 minutes or as long as you like, and that evolution would therefore be inbuilt in what the system was. There is no role, it seems, for free will. Do we have a role for free will here? Well, not as it stands, because it's meant to be just probabilities. So there has to be more than that if you're going to find a role for free will. But at least it does open the door for a possible role for free will, whatever that means. Let me continue. I should also mention, which I think I mentioned in the last talk I gave, is that the collapse of the wave function, in my view, is not due to the conscious observer looking at the state. So there were people like von Neumann and Wigner who took the view that it was the conscious being, the external conscious experimenter, looking at the alternatives that your experiment seems to produce, and it's the observer looking at the system which reduces the state. I'm not taking that view at all. I'm taking the view that it has nothing to do with the conscious observer observing it. It's really the other way around, that whatever consciousness is somehow takes advantage of what the collapse of the wave function is. Now, in this slide, I'm indicating the point of view introduced originally by Dioschi. A couple of years later, I independently thought of it using a different type of argument from his, which I outlined in my previous talk. And it tells you, if you have a superposition between two bodies, or at least a body and itself in a different location, say, the body over here and the body over there, and it's a superposition between those two states, then that state doesn't remain in that superposition forever, but there is a lifetime. If it's very, very tiny, then the lifetime will be very, very long. If it's large, then the lifetime will be short. And the formula comes about from this quantity Eg. Eg is the gravitational self-energy of the difference between the two states. I want to say a little bit more about that Eg. Here I have a little calculation one can do. Here I'm imagining you've got a uniform sphere, and this uniform sphere is put into a superposition of being in one location and another. So at the top you can see the sphere in one location, and the dotted one is the sphere in the other location, and that would be a quantum state, that it could be in that state. Now, what is Eg? You can do a little calculation of what Eg is, and I have a graph of it at the bottom. When the two are completely on top of each other, with an Eg is 0, as you start to pull them apart, then you see this curve right at the bottom of this picture goes up as you move them apart until the dotted line there is when they're in contact, and then it still goes up as you move them apart, but not by so much. So that gives you a picture of what Eg looks like for a sphere moving apart like this. Okay, well, now, here I have a space-time picture of that. I'm imagining time is going up and the sphere is represented by this vertical line right at the bottom. So it's in one place. And then as time progresses, going up the picture, time you can think of as represented by horizontal slices of this picture as they go up, then you start to separate them apart, and after a certain time, this time h cross over eg, that h cross is Dirac's form of the Planck's constant, and that tells you the order of time which it would take for it to collapse. And so I'm supposing that where these dotted lines cease and one of these things becomes the world line of the actual particle, so it's right at the top, you see that the body has gone into the superposition of two, and then the collapse takes place, and it becomes the left-hand one in this picture. It might have been the right-hand one, but it was the left-handed one in this case. Now, there's something a little puzzling about this picture when you consider relativity. Because in relativity, there isn't just a time which plods along and is represented by the horizontal slices moving up in this picture, but depending upon the sort of state of an observer, sort of an impartial observer moving along and looking at the whole thing, if the observer is moving from left to right, then you would take the T slices, which tilted upwards to the right. If the observer is moving from right to left, then according to that observer, the time slices would be tilted in the other direction. Now you have a bit of a problem here, because if the body has disappeared, you see the dotted lines of the world line now become a superposition of those two possibilities, and you have the point Q and the point Q star. And what I'm saying is that what it collapses to Q star. Now, in the reference frame that I started with the horizontal lines representing the progression of time, then as soon as one has disappeared, the whole state becomes the other. But now, according to these moving observers, that doesn't work. The T observer, which is moving to the right, it's as though the one has disappeared before the state has become entirely the other one. So that as far as that observer is concerned, there's still a chance that the other one might disappear too, and the whole thing might disappear. That's ridiculous. It doesn't make any sense. And you might consider another observer moving the other way, and then the whole state has become Q star, when there's still a possibility that it might be Q. So it doesn't make any sense. The picture just doesn't work for the other observers. So how do you make the picture work? Well, the only way I can see, I would say there is one bit of a possibility too, which I have to consider, but I'm going to say the only way that really makes sense is that the collapse goes right back to the original point, and that when the collapse has happened, in a certain sense of when, it actually goes back retroactively to the point O. So when the collapse decides that it's going to be the left-hand branch, the Q star thing, it's as though the reality goes back to O. This is actually what I'm calling classical reality. In order to make sense of all these ideas, you really have to have two kinds of reality. You have to have the classical reality, which sort of goes back to the origin point, or it goes to the the other one disappears in this view. So it goes back to the origin point, and the decision, in a certain sense, of which it is, has to be made at the point where they start to separate, which is a bit of a strange picture. There is a sort of loophole to this, which I did think about. Philip Pearl and various people consider a thing that they call gambler's ruin, and you have an amplitude which sort of wiggles around attached to these two dotted things in the middle of the picture, and when one of them gets so much bigger than the other that you say, well, you more or less consider that it's happened, that it's what they call gambler's ruin, that they're gambling against each other, and then one of them has so much money that the other one might as well give up. It's not terribly clear when the give-up takes place, and that's the problem I still have with it. But nevertheless, it takes it to a different level, and you might consider that the amplitudes are wiggling around independently, and then one gets too small, then the other one becomes the real state. I don't think it really resolves this issue, and I'm pretty sure it doesn't from various other arguments which I can't really give you here. But there is a problem that if you don't take the collapse to be at the initial point where they start to separate, you have a bit of a problem for saying when the reality takes place. Now, I'm taking the view that this is classical reality.